All right. Hey guys, it's Levins here, and I am here to read to you from Earthquakes. I'm going to read this whole book today, and there's a reason. Normally we just read a couple pages, but today I'm going to read this whole thing because on your slides today you are going to be talking about how this book was similar to the book that we read in the text collection called Quake, and basically what you're going to do is you're going to answer some questions. So this first question says, what details about earthquakes are similar in the two texts? And then you're going to think about why you think we read this book before we read Quake. And the second slide has you summarizing this. So really, overall, what was this book about in 2 to 3 sentences? So, for example, if like your sibling came to you and said, "What's that book about?" you would tell them in 2 to 3 sentences what this book is about, just kind of in summary or in general. And then you'll do the same thing with Quake. So, without further ado, my friends, here is Earthquakes by Seymour Simon. I really like this guy's name. Let me just get on the right page here. All right. All right. This page here, picture, and then the next one. All right. The earth beneath our feet usually feels solid and firm. Yet 1,000,000 times each year, an average of once every 30 seconds, somewhere around the world, the ground shakes and sways. We call this an earthquake. Most earthquakes are too small to be noticed by people. Only sensitive scientific instruments record their passage. But hundreds of earthquakes every year are strong enough to change the face of the land. A large earthquake in Kobe, Japan in 1995 toppled this freeway on its side and cracked the roadway in numerous places. This picture is an example of the enormous destruction an earthquake can cause in a heavily populated area. Next page. On the morning of September 19th, 1985, a major earthquake struck Mexico City. It killed 10,000 people and injured another 20,000. Hundreds of buildings were destroyed, including homes and stores, hotels and hospitals and schools and businesses. This multi-level parking garage, centered right, collapsed like a house of cards. Ooh, that's a simile. While some of the neighboring buildings suffered only slight damage. Here is the building to the right. And feel free to pause this at any time. If you are looking for details or something, you can always pause on the text if you don't have the actual book and grab the detail from the text on that page. Next page. Most earthquakes take place in the Earth's crust, a 5 to 30 mile deep layer of rock that covers our planet. Cracks in the rocks, called faults, run through the crust. In one type of fault, called a strike-slip fault, the rocks on one side of the fault try to move past the rocks on the other side, causing energy to build up. For years, frictions will hold the rocks in place. But finally, like a stretched rubber band, the rocks suddenly snap past each other. The place where this happens is called the focus of the earthquake. From the focus, the energy of the earthquake speeds outward through the surrounding rocks in all directions. The shocks may last for less than a second for a small earthquake to several minutes for a major one. Weaker shocks, called aftershocks, can follow an earthquake on and off for days. Sections of the crust have slipped past each other along 2 strike-slip faults and offset this ridge in Wyoming in the left picture. Sometimes one side of the fault will slip up over the other. This is what happened along this highway in the Mojave Desert of California on the right. This kind of upward movement is called thrust fault. When I think of that, so on page 8, it talks about how from the focus of the earthquake, the energy speeds out in all directions. I think about when you throw a rock into the water, how that ripple kind of goes out in all directions. I imagine that that's kind of what an earthquake does. It speeds out in all directions. Next page. 4 out of 5 of the world's earthquakes take place along the rim of the Pacific Ocean, a zone called the Pacific Ring of Fire. Alaska, Washington, Oregon, California, Mexico, the west coasts of Central and South America, and the east coasts of New Zealand, the Philippines, Japan, and Russia, Kamchatka, and the Kurils are all located along the Pacific Ring of Fire. Another major earthquake zone stretches through Italy, Greece, Turkey, and Armenia to the Middle East and into Asia. In the United States, almost half of the earthquakes each year occur in Southern California. In other sections of the United States, earthquakes are rare. And here's the map that they are talking about that shows you, see how right along California down here kind of looks like a thumbprint? That purple shows us where a lot of our earthquake activity is. All right, and then here's a picture of earthquakes from around the world. Each of those little red dots indicates a place where an earthquake has occurred. Why do most earthquakes in the United States occur in California? That answer lies deep within the Earth. Our planet's solid rocky crust floats on the mantle, a 1,800-mile thick layer of very hot and dense rock that slowly churns around like a huge pot of boiling soup in very slow motion. It's another simile. It's comparing the molten lava to a bowl of soup or a pot of boiling soup. Ugh, that sounds hot. The slowly moving mantle carries along the solid crust, which is cracked like an eggshell into a number of huge pieces called plates. The plates float slowly about on the mantle up to 4 inches a year. As the plates move, they run into or pull away from each other, producing enormous strains in the rocks along their edges. The United States and Canada are riding on the North American plate, which is slowly moving against the Pacific plate, which makes sense because we live in North America and we live, especially in Washington, right next to the Pacific Ocean, which is the Pacific plate. The colliding plates cause most of the earthquakes along the West Coast. But earthquakes can occur anywhere there is stress. There are stresses in underlying rock. The San Andreas Fault is the boundary between the North American and the Pacific plates, the ones we just talked about. It winds 700 miles through Southern California to just north of San Francisco, where it heads west across the floor of the Pacific Ocean. Along the way, it slashes under houses and dams, across deserts and farms, and through towns and cities where more than 20 million people live. Dozens of small to medium-sized earthquakes occur along this fault each year. Scientists think that a huge, deadly earthquake will strike along the San Andreas Fault in the near future. It's a picture of the fault line. That's a beautiful picture. Next page. The 1906 San Francisco earthquake was one of the most violent earthquakes ever recorded. I'm pretty sure that that's what we read about in Quake. It was felt over an area of 375,000 square miles, more than twice the size of California. More than 3,000 people lost their lives in the earthquake and the following fires. This view shows San Francisco in flames hours after the earthquake. The fires alone destroyed 28,000 buildings in the city. That's a lot of buildings. That is a lot of buildings. This fence was broken and offset 8 feet by the movement of the San Andreas Fault during the 1906 earthquake. Besides the widespread strike-slip, side-to-side motion along the fault above, there was also vertical movement of as much as 3 feet in some places. And this is kind of a cool little feature here. I can show you what it looked like. So here's before. And then, hold on, I gotta read the instructions. Slide the bar. Okay, so this bar here. This bar? Oh, that, like that. Ooh, see how it changed? So that's what the fence looked like before. And then after, that's how much the ground moved to offset that fence. Like, it's not like the farmer just was like, hey, I want a door here. I'm going to open that fence up. No, that's not what happened. The earthquake came through and moved that fence back. That's crazy. That's a cool picture. And thank you to Reagan for showing me how to do that. That's very cool. And next page. How do you measure and compare the sizes of earthquakes? The size cannot be judged solely by the damage to buildings or the number of people killed. That's because a medium earthquake close to a large city will cause more destruction than a larger earthquake in an unpopulated area. Seismographs are the instruments that scientists use to measure earthquake shocks. Modern seismographs record their data to a computer and are able to detect a tiny earth tremor thousands of miles away. Seismologists Oh, I can't ever remember how to say his first name, but his last name is Johann, of Germany's Geoscientific Research Institute, points to the shockwaves that were recorded in blue in this digital graph on the right of March 28, 2005 earthquake off the island of Sumatra. There are hundreds of seismograph stations all over the world that time the arrival of earthquake waves. Scientists use measurements to find the earthquake timing, magnitude, and location, the latitude, longitude, and the depth. And here's a picture of this guy reading the seismograph. You can see those blue lines indicate an earthquake. Next page. Scientists use the Richter scale. Scientists use the Richter scale to measure an earthquake's magnitude, or the amount of energy it releases. Each number on the Richter scale stands for an earthquake that is 10 times more powerful than the number below it. You would hardly notice a magnitude 2 earthquake, but a magnitude 3 earthquake is 10 times greater and easily felt by everyone. The scale has no upper end, but any earthquake that registers 6 or more is considered a major earthquake. The earthquake off the island of Sumatra on December 26, 2004 registered a 9.0 magnitude and caused huge earthquake-formed sea waves called tsunamis. The enormous earthquake and tsunami waves killed more than 200,000 people and caused immense destruction in several countries. Some of the destruction it caused. Somebody's bathroom still hanging out there. Next page, some more destruction. This destruction that you see is from the San Francisco area in 1989. We're going to read more about that in just a second. Scientists use observations as well as instruments to measure the effects of an earthquake. The Mercalli intensity scale uses observations of the earthquake damage to rate it on a scale ranging from 1, where the effects are scarcely noticeable, to a 12? Yeah, that's 12. XII in Roman numerals is 12. The X stands for 10, and then each I is 2, so 10 plus 2 is 12. Where damage noticeable to a 12, where damage is total and the ground heaves in waves. Usually the intensity is greatest near the center of the earthquake and smaller farther away from the center. But other factors, such as the soil in the area and the constructions of buildings, are also important. For example, the earthquake that shook the San Francisco area in October 1989 during the World Series measured a 7.1 on the Richter scale. On the Mercalli scale, it measured a 10 to an 11 in the Marina district, shown here, where the houses are built on loose soil, but only a 6 or a 7 in other parts of the city, where the houses suffered much less damage. Sand, mud, and water sometimes boil up during earthquakes, gushing water and soil like miniature mud volcanoes. These sand boils are particularly dangerous to buildings. In places where water is close to the surface, sandy layers turn into quicksand, and buildings tilt and crumble. During the 1989 San Francisco earthquake, sand boils erupted in basements, in yards, and beneath houses all over the Marina district. These houses in Niigata, Japan, tilted and tumbled as a result of an earthquake in 1964. The buildings tilted when the soil beneath the foundations turned to quicksand. About a third of the city sank by as much as 6 feet. That's taller than me. More than me. Next page. On the afternoon of Good Friday, March 27, 1964, Anchorage, Alaska was shaken apart by the most violent earthquake ever recorded in the United States. It measured an 8.4 on the Richter scale. Government Hill Elementary School was split in two when the ground beneath it dropped. Houses began sliding apart, giant cracks opened in the pavement, and the ground rolled in huge waves. In the first 3 days after the earthquake, 300 aftershocks shook the buildings that remained standing. I think this is a picture of the elementary school. And this is a picture of the Prince William Sound in the Gulf of Alaska. See the boats? The Good Friday earthquake brought another type of destruction along the coastline. The focus of the earthquake was deep beneath the waters of the Prince William Sound in the Gulf of Alaska. The earthquake acted like a giant paddle churning the waters. Tsunamis battered the land for hours. An entire section of the waterfront at the port of Seward cracked off and slid into the ocean. Boats were overturned, buildings broke apart, and everything was left in a tangled mess. The tsunamis moved across the Pacific at speeds of hundreds of miles an hour, reaching as far as Hawaii and even Japan, 4,000 miles away. Scientists have learned much about earthquakes and their effect. They can measure even the slightest movement along faults. But we need to know much more about earthquakes before we can predict weeks or even days in advance before a big one will hit. Until then, proper building design can help lessen the effects. We now know that houses in earthquake-prone areas should be built on solid rock and not on sand. For example, in California and Japan, new houses are designed to be earthquake resistant. It also helps to know what to do when an earthquake strikes. If you are indoors, get under a heavy table, desk, or bed. Stay away from windows, mirrors, or high cabinets. If you are in a high building, stay out of the elevators and stairways. If you are outdoors, move away from high buildings, walls, power poles, and any other tall objects. If possible, move to an open area. Above all, remain calm and don't worry. The chances of you being hurt in an earthquake are very, very slight. I know in my classroom, we talked a lot about how we can keep ourselves safe in an earthquake and why we practice, right? We practice so that way, in the case of an emergency, we already know what to do, so that way we don't panic and end up just being afraid. We can actually make moves to protect ourselves. So that was Earthquakes by Seymour Simon. Feel free to use this video, watch it again, scroll through, fast forward to parts that you need, and look for those key details to answer your questions for your slides. You guys are rad. Keep working hard. We're proud of you.